ICE tables. So say we're given a chemical reaction with a KEQ value. So for the reaction between H2 and I2 to make HI, at a particular temperature we've got a KEQ of 45.9. So let's say you take a reaction vessel and you put 1 mole each of H2 and I2 in it. What's the concentration of everything at equilibrium? To do this, you need to make an ice table. I stands for initial, C stands for change, and E stands for equilibrium. So, for each of our reactants and products that's in the gas phase or the aqueous phase, we have a value. And 3 lines, I, C, and E. The initial values are what you start with. So, we have 1 mole each of H2 and I2. And you really want the concentration. But, okay, let's say the reaction vessel has a volume of 1 liter. Then our concentration will be 1, 1, and 0. Okay, now the change. Well, we only have reactants, we have no products. So we know that some of the reactants will be converted into products. The concentration of reactants will go down. The concentration of products will go up. But by how much? Well, we don't know, but we do know the relative amount. So say H2 and I2 both decrease by some amount we'll call X. The change line for H2 and I2 will be minus X. Then the change line for HI will be plus 2X. Why 2? Because the coefficient on HI is 2. The equilibrium value on the E line is just the sum of the I line and the C line. So we've got 1 minus X, 1 minus X, and 2X. Now, to use this, we also need an equilibrium expression. So, our equilibrium expression is concentration of products raised to their coefficients over concentration of reactants raised to theirs. We're going to have, on top, the concentration of HI squared. On the bottom, we will have the concentration of H2 times the concentration of I2. Now we plug in the equilibrium values. Into this expression. So we have on top 2x squared over 1 minus x times 1 minus x. So we get 4x squared over, now we have to FOIL the bottom, 1 minus 2x plus x squared. And we set that equal to the KEQ value of 45.9. Now we can solve for x. So from here, I'm going to multiply both sides by the denominator. So 1 minus 2x plus x squared and 1 minus 2x plus x squared. And we get 45.9 minus 91.8x plus 45.9x squared equals 4x squared. And we want this to be in the form ax squared plus bx plus c equals 0. So we'll subtract 4x squared from each side. And so we get 41.9x squared minus 91.8x plus 45.9 equals 0. So, 41.9 is A, negative 91.8 is B, and 45.9 is C. We now use the quadratic formula to solve for x. X equals negative b plus or minus the square root of b squared minus 4ac over 2a. Plugging in these values of a, b, and c to the quadratic formula, we have x equals 91.8 plus or minus the square root of 8,427 minus 7,693 over 83.8. The square root becomes 27.1. So that means that x equals 91.8 plus 27.1 over 83.8, or x equals 91.8 minus 27.1 over 83.8. And we know this is the only possibility because this will give us a value less than 1, and our initial concentration of both of our reactants was 1. And so if we used the other value, which is greater than 1, that won't work because we'll end up with a negative concentration. This gives us a value of x equals 0.772. So if we go back to our ice table, we had the equilibrium values of H2 and I2 at 1 minus x, and HI was at 2x. So if we plug in 0.772, 1 minus 0.772 is 0.228. So the concentration of H2 equals 0.228, and the concentration of I2 equals 0.228. And then the concentration of HI is 2 times that, 2 times 0.772, 1.544. That's the concentration of HI. And if you remember our equilibrium constant expression, we had the concentration of HI squared up top over the concentration of H2 times the concentration of I2. So plugging in those values, we have 1.544 squared over 0.228 times 0.228. Which gives us 45.859, which, if you will recall, was the given value of KEQ.